Well, hi, I'm Mr. Levier, and I'm here with good friend Bob Boisvert, who is interested in all kinds of science. And today we're going to learn about the electromagnetic spectrum, and we're going to learn about fluorescent minerals. How are you doing, Bob?
I'm doing great. How are you?
Good to see you.
Always.
So, Bob, tell us how you got involved with fluorescence and fluorescent minerals.
Well, I've been collecting rocks for a long time, and some of those included fossils, and I did go out with Mr. Leveille many times to go looking for rocks. A couple of years ago, 3 or 4 years ago, a friend of mine said, "Here, I got something to show you," and I had no idea what the guy was wanted to show me at the time. So he turned the lights off and turned on a display, and he showed me his fluorescent mineral collection, and I was smitten. It was so impressive. I had to find out more about it, and better yet, I had to get some of my own. So I started reading about it. I started collecting and buying some fluorescent minerals and learning about it in the process.
All right, so can you explain a little bit about what fluorescence is?
Well, to be able to do that, I think one of the first things we have to do is talk about light. And in 1600s, there's a fellow named Isaac Newton, which took a prism, something like this over here, and using this, he was able to produce a rainbow. And he realized that the rainbow were basically all of the light coming in as white light, or what they perceived as white light, and it was broken down into these various components. I only have one prism, but what Mr. Newton did is he took two prisms, and he put white light into a prism. It came out as a rainbow, and he put the other prism at the other end. It came back as white light. So yes, white light is actually constituted of all of this different light. The light that we see from violet to red is actually, we can measure that particular light. It's coming to us like little waves, and we know very precisely how long these waves are. The violet light is on the shorter end of this, and the red light is at the other end. Now, you'll notice on the diagram that Mr. Leveille will show you in this presentation that ultraviolet. So we cannot really see it. We can't see ultraviolet light, but it's there. It's sitting just before the violet side of things. And at the other end, past the red, we have something called infrared. Now, the way we measure these waves, it's like any wave that you have in a lake or in the ocean, and you have some waves that come and go and come and go. And the way we measure them is from the top of the crest of the two waves, and that will give us the wavelength. Light is actually measured in nanometers, which is really, really, really small. So it's 1 dot and 8 zeros and a 1, I believe. So it's really, really a very small number, nanometers. That word is very important because it'll come up in the next few slides. Our eyes can only see between 300 nanometers and about 700, so from violet to red. Some children, some very young children, can actually see some of the ultraviolet spectrum, but don't do that. It's a very bad idea to look at the ultraviolet light because it can damage your eyes, so we should never look at it. We can feel the infrared light as heat when we're out in the sun and you're feeling heat. That's the infrared actually toasting your skin a little bit. We do need a little bit of ultraviolet light because when it hits our skin, just a small amount of it, we're talking just a few minutes, will be able to create vitamin D in your body, and we need vitamin D for our bones and teeth. Ultraviolet is measured also in nanometers, and it's in the range of 100 to 400 nanometers, and it can actually be divided in three parts. UVA, which is between 315 and 400, UVB, which is 280 to 315, and UVC, which is the short end of the spectrum, is between 100 and 280 nanometers. The most dangerous one is UVC, but we are not exposed to much of that in our daily lives. There's actually all three kinds that are coming from the sun. So the sun does send UVA, UVB out our way, and when you're applying sunscreen to your skin, you'll notice on the package it says this will protect you from UVA and UVB. But what about UVC? Well, that one pretty much never reaches us because the ozone layer in the sky is protecting us from that. So we don't get much of it coming our way. To be able to describe how fluorescents actually work, we have to understand a little bit about atoms. So the slide that Mr. Leveille will show you now shows you a model of what an atom looks like. An atom is the smallest unit of matter with you. So and actually in everything around us, you've heard of carbon and oxygen and hydrogen. These are all different types of atoms. In the middle of the atom, you've got the nucleus, which is contains positive protons and neutral neutrons. And swinging around that, you've got a cloud of electrons. And it's the electron that is involved in this fluorescence. Mainly the ones that are sitting on the outside of an atom. So if you have an atom that has an electron which is a little more free than the other electrons around the atom, it might give us some fluorescence. So what happens? And this diagram is pretty important. You've got the ultraviolet light which is coming at an atom. If there's a free electron on the outside of the atom, the photon will hit the electron and actually kick it up at a higher energy level. Electrons are actually, they're like tracks going around the atom, and they only like to be in those tracks. They don't want to be anywhere else. They don't want to be halfway between two tracks. So the electron hits it if it's the correct amount of energy, and then it'll go up one track in the atom. It can't stay there. The electron doesn't have enough energy to stay in that position, so it's going to be returning to where it came from. And when it does that, it'll shoot another little piece of light called a photon at a different wavelength than the one coming in. So it came in as ultraviolet, you can't see it, but it kicks it out with less energy. So it's going to be violet or green or yellow or red at a much lower energy. That's basically how fluorescence happens.
That's amazing. And so tell me about how minerals connect to fluorescence and the atom.
Well, the minerals, they're made up of atoms, and some of the minerals have electrons that are a little freer on the outside of that composition that they have. So about 15% of the known minerals, and there's about 6,000 minerals that are known at this point in time, minerals like calcite and afganite and all kinds of minerals, and only 15% of them will fluoresce, because only 15 of them have got sufficiently mobile electrons that can actually be knocked up and down in this fashion and produce light. We can buy flashlights which are specifically created to create UV light. And so they're a regular flashlight like any other, and there's a LED inside which produces the energy. But if you look at the end, you'll see that there's a black filter in front of it. And the reason why that black filter is, the LED inside also produces a little bit of white light and red light and whatnot. So this filter only lets the exact wavelength out of it. Now, there's different kinds of flashlights that have been created over time. This one is very common. It's easy to get. It's not expensive. UVA, the long wave. And you can also get UVB, medium wave, and UVC, short wave. And I've put some colored tape on it because I've got so many lamps in my collection that I have to keep track as to which one is what kind of wavelength, seriously. So, but they all produce UV light for my benefit. And why have three lights? Well, the minerals don't react the same. Some minerals will only react with the long wave or only with the short wave. And the medium wave, more or less practical because the only thing it's useful for is mostly calcites. But so it's nice to have all three lamps. And I'll have a special treat at the end of the presentation because I'll show you a mineral that behaves differently at each one of the different wavelengths. So it's one color for this one, a different color for this, and a different color again for that same piece of rock. Absolutely spectacular. Now, there's other things that happen too. So far I've described fluorescence. And by the way, fluorescence was named like that because the first time that it was observed, it was with a piece of fluorite. So this is a piece of fluorite over here. We'll take a look at it with the lamp a little later.
Can I see?
Yeah.
I just want to take a look at it. Wow. You can see the cubic structure on it.
Oh, fluorite is very, very nice. And it's got different types of structures possible.
Beautiful.
So fluorite was the first one that was discovered to have this effect. And later on they found that there were all kinds of rocks that were also had this effect. Now, there's another effect that you can see with fluorescent minerals, and this one's called phosphorescence. The word comes from one mineral or one element called phosphor, and basically with this element, the fluorescence mechanism is exactly the same, except instead of becoming excited and coming back to neutral immediately, it basically stays lit for a fraction of a second, a couple of seconds, and even as much as 2 hours. So the phosphorescence is the same deal, except it lasts longer. There's another one, very uncommon, which is called tenebrescence, and that is absolutely drop dead spectacular. So it's like fluorescence, except when the UV light hits this particular type of rock, mostly hackmanite, the rock will become purple and stay purple. So it changes color from what appears to be white to purple, and then it'll stay like that until it sees the sun again. So the sunlight will kind of erase all the purple, and then you can start over again, expose it to UV light, and you can almost write your name in the rock with this. So it's actually really, really spectacular. And the last bit of fun, this one is a bit of a mouthful. It's called triboluminescence. So basically, if you strike two pieces of quartz together, you'll see a little bit of light coming out. And no, it's not a spark. It's not a spark, so you can't make a fire with that. If you wanted to make a fire, you would need to find flint and a piece of metal to strike against it. But when the quartz hits, what happens is that some electrons that I described earlier are ripped out of the atoms, and then when the rocks separate, the electrons go back where they were. So it'll create a little bit of light in doing so. It's not fluorescence, but it's sort of kind of related to that anyways, and I think it's a lot of fun. And the another way of seeing this triboluminescence is to crush wintergreen lifesavers in the dark, and you'll see that effect as well. So that's fun, and it's actually very tasty. So. Other things that fluoresce, and I'll show you some samples of that too, You can have a passport, has actually very spectacular fluorescent in it. Tonic water, it's not soda water, it's tonic water very specifically. If you put a long wave lamp to it, it'll glow blue, light blue, and it's fun to watch. It's a nice party trick to do. Some seashells, if you put a UV lamp to it, they glow beautiful red, so it's kind of interesting. I even found some fossilized seashells in Florida, and if you look at them, they are 50 million year old seashells, and you look at them and they're white, and when you shine the UV lamp on them, they turn bright orange, so it's kind of spectacular. Yeah. What else? Lichens. So when you're looking at the trees, Mr. Leveillé can show you what lichens look like. And if you flash a UV lamp at them, they glow yellow, orange, and red. Kind of spectacular. Some country money have got fluorescent stamps on them, official documents, plants. If you walk around at night with a UV lamp, boy, the plants, they light up red. It's just spectacular. And uranium glass. So there's a type of glass that they produced about 100 years ago. It contained little traces of uranium, and the glass itself is green, but when you put the UV lamp on it, they light up in the night.
Well, that gives a whole new perspective to a late night meal.
Yeah, absolutely.
Well, thank you, Bob, and we're going to be looking at some samples now. This is really exciting. So these are Franklin, New Jersey minerals. The calcite is the red or orange, depending on who's looking at it, and the green is willemite.
Yes.
And the dark is franklinite.
That rock over there is hardistonite. So if you turn it, you'll see kind of yellow in it.
Yes, I can see that. Alright, so we're going to turn this purple. Awesome.
That should be good.
Oh, look at that. That is a nice shade of purple.
I like to call it my magic rock.
Oh, nice.
Now it's going to stay purple like that until it's exposed to sunlight, or just leave it in the room. It's going to disappear over time. But this is called tenebrescence.
That is really cool. I never heard of this before. Oh, it's always fun to learn something new.
Yeah. This is my favorite rock. It contains sphalerite with possibly Cleophane variety of fluorite on it. So it fluoresces 3 different colors.